Happy National Day! Better education, better nation. Welcome to our calculus series with GeoGebra using the reference textbook by James Stewart. This is our 5th lecture in chapter 3. Last lecture, we visualized the formation of a rainbow in 2 dimensions. We assumed the sunlight is parallel to the Earth's horizon. This assumption is valid and convenient if our purpose is limited to find the biggest angle of elevation from the observer, often referred to as the rainbow angle. We successfully find it to be roughly 42 degrees. But this assumption does not always hold true. The sunlight is not always parallel to the horizon. In fact, the sunlight forms an angle with the horizon, technically named sun altitude. We can call it the sun angle. Let's explore how this angle is related to the visibility of a rainbow. Here are 2 models. The 2-dimensional model is on the left side. The 3D model is on the right side. This 2D model simply shows a raindrop in the shape of a circle. The sunlight refracts into the drop at point A, reflects at point B, then refracts out at point C. Due to slight difference of refractive indices of each color, we can recognize 2 paths, one for red and the other for violet, resulting in viewing angles of 42 degrees for red and 40 for violet, etc. Look at this slider, sun angle. By default, it is initialized at 0. Now try toggling the slider. We can see this angle is getting bigger. In the 3D page, the sun is moving up. When the angle is increasing from 0 to 42 degrees, the rainbow becomes less and less visible. It fades away. At around 40, violet and blue bands disappear first. At around 42, the rainbow is completely invisible because it is totally below the horizon. During this animation, you might have noticed the colorful rainbow can be seen as a group of concentric circles around a special point, the anti-solar point. It lies opposite the sun in the direction of your shadow. When the sun moves up, the anti-solar point moves down, and vice versa. The line from your eye through this point forms the rainbow's axis, which will be explained later. Now we zoom in to observe the cross-section of the 3D model, the meridian plane. Compare the models on both sides. On the left, we see 2 rays coming out from a single drop. On the right, we also see 2 rays of the same colors, but from 2 drops differing in their heights. The higher drop is colored in red, sending a red ray towards you. Apart from the red ray, does this drop have a violet ray? Mathematically, yes, the violet ray exists. Physically, no, you cannot see it. Where is the missing violet ray anyway? How about ticking this checkbox? We now show the ray which is invisible a moment ago. It is no longer a mystery. we confirm that the violet ray is also coming from this higher drop. It just ends up too high to reach your eye. Only the red ray is exactly reaching your eye, neither too high nor too low. If we rotate such a red ray around that axis, we get a red cone. Decrease its opacity, and we can see the hidden colors. Each color corresponds to a cone. All these cones share the same apex, the same axis. These cones differ only in their opening angles. As a result, red cones look a bit wider than violet ones. Imagine, after a rain, a thin curtain of raindrops is set perpendicular to the cone's axis. Where a color's cone meets this curtain, it draws a circle. The horizon cuts that circle into upper and lower parts. From the ground, we are only able to see the upper half at most when the time is near the sunset. But if you are high above the ground, on a mountain or in a plain, you can expect more than a half, sometimes even a full circle of rainbow. This can be easily visualized so long as we increase the Z value of our eye. And here is how the full rainbow looks in reality. Look out over the plain wind. The lower part of the rainbow is no longer blocked. The brighter ring with red on the outside and violet on the inside is our familiar primary rainbow. Just beyond it, we can spot a fainter ring with the colors flipped. That's the secondary rainbow, which also has a beautiful name in Chinese. Now back to our own rainbow. Despite being a little fainter compared with the primary rainbow, the secondary rainbow is still obvious, isn't it? Now pay attention to the time and the place of the photo. That photo was indeed taken in a late afternoon in summer, when the sun was getting very low, about to set, and thus near the horizon. We can even check this by the amazing website, getting the exact information of the sun in this particular place on this particular day. As our mouse cursor moves towards the right-hand side, the sun attitude angle continues to decrease. Between 1826 and 28, the angle is about 4 degrees, which is close enough to 0, which corresponds to the sunset time at 1850. Rainbow has fascinated humans for millennium. Great minds from Descartes to Feynman are inspired by its beauty. Here is a page from a biography of the great physicist titled Feynman's Rainbow. Hopefully, you can be inspired as well by visualization using modern tools and by the beauty of nature. Better education, better nation. Happy National Day.